The topic is Anorthosite and Alkaline Magmatism and associated mineral system. I just added this mineral system because today's era is for mineral system and ore deposits, auctioning, etc. So I just added. But so as to say that Anorthosite is not much that potential, whereas Alkaline Magmatism is always potential. You know this. Now, first, my topic is comprises two parts: anorthosites and alkaline magmatism. And these are completely different rocks, different composition. Petrogenesis is different. Tectonic setting is more or less different. So, so I will be dividing these into two parts: anorthosite, first part, and then alkaline magmatism in the second part. In case of anorthosite, I will be emphasizing on the petrogenesis aspect. In case of alkaline magmatism, I will be emphasizing on the mineralization aspect. So this will be my presentation for this evening. Starting with anorthosite, everybody knows anorthosites are plutonic igneous rocks. The important thing is that they contain more than 90% plagioclase. These can be called as monomineralic rocks. When any rock comprises more than 90% of same mineral, then it can be called as monomineralic rock. And moreover, the plagioclases, their calcium content, we call it as anorthite content, ranges from about 40 to 90%. The rest, less than 10%, they are mainly high temperature ferromagnesian mineral phases, like pyroxene, olivine, and FETI chrome oxides, like ilmenite, magnetite, chromite, like these things. So these monomineralic rocks are mostly, they are the cumulates. As you can see from the photomicrographs, which is very obvious, the feldspars or plagioclases, they form the cumulates, and the ferromagnesian phases, they are mostly the intercumulus phases. Sometimes they will be less than 10%. Sometimes they may be more than 10% by more. Then the name will change. So first of all, I will like to introduce the classification of the anorthositic and the related rocks. As you can see, the mineralogy, as I said, it comprises plagioclase and mapping minerals, which are orthopyroxene, clinopyroxene, and rarely they are olivine also. So based on that, this triangular classification diagram is given. As you can see here, 90% or more, they are called as anorthosite. But when the olivine or olivine or pyroxene increases, the name changes to leucogabbro or leucotroctolite, gabronorite or troctolite, and melanogabbro to melanotroctolite. So the terminology is based on the moral proportion between the ratio of the moral proportion between the plagioclase, and on one side it is pyroxene and other side it is olivine. And as we see here, all the rocks are anhydrous rocks, dry rocks. There is no phase which contains hydroxyl component is involved in this mineralogy. So the anorthosites are normally the rock associated with rocks like leuconorite, leucogabbro, leucotroctolite, like this, and the ultramafic component is usually rare. So, but maybe present in some complexes reported very minor components, or maybe absent. If somebody can mute his mic, it will be very convenient for me to continue with the presentation. The anorthosite rocks are not only abundant on the earth, not much abundant on earth, but
all participants are requested to mute their audio.
Thank you very much. So the anorthositic rocks are not very abundant. They are very rare complexes, except at few places. But but these are very dominant lithology in the moon and some other planetary bodies like meteorites. Their mineralogy is more or less similar to basalt. If we see a basalt, it also comprises pyroxenes, plagioclase, and plus or minus olivine. Similarly, anorthosites are plagioclase plus pyroxene plus or minus olivine. Only thing is that in the basalts, the moral proportion of pyroxenes will be more or equal to the plagioclases, whereas in case of anorthosite, it is more plagioclase, dominantly plagioclase compared to pyroxene. So now coming to the type of anorthosites, as I said, the terrestrial anorthosites, we can divide them into first terrestrial anorthosites and the planetary anorthosites. So we can classify them. The terrestrial anorthosites can be your Archean anorthosites, Proterozoic massive type anorthosites. Some anorthosites are associated with layered mafic intrusions. Thin cumulates, they may occur in the ophiolites, small xenoliths, lunar highland anorthosites. So these 6 types, as you can see here, the last one is basically a planetary anorthosite, mainly occurring in the meteorites as well as moon. The rest 5 are terrestrial anorthosites. Among the first 5, Archean anorthosites and Proterozoic massive anorthosites are more or less very important for us phylogenetically, though layered complexes are also known to them and known to us. They comprise anorthosites. And out of these 6, 3, including the lunar highland anorthosites, they have formed during a very limited period of time in the solar system history. The Archean anorthosites, as the term indicates, they are formed in Archean. Proterozoic anorthosites or massive type anorthosites, they are formed during the Proterozoic period, and lunar anorthosites are formed during the formation of the moon itself, early part of the moon. So they do have some time, restricted time. Their formation is to a restricted time. When some rocks they form in a restricted time, that must indicate, they are always indicate some kind of special character that was existing during the evolution of the earth and the planetary bodies. So something has happened during that period of time which facilitated the formation of such kind of rocks during the evolution history or solar system history. Now coming to say very briefly, I would like to touch the lunar anorthosite. These are dated. The samples have been collected and they are dated to be between 4.3 to 4.6 gigaannum. And these are mostly, as you can see this moon picture, that is a far side of moon taken by NASA. The lighter highlands, basically, lighter colored heavily cratered regions are dominated by the anorthositic rocks. And what the researchers, they say that these anorthosites in the moon, they comprise, just like our crust, the lunar crust is comprises of anorthosites. And they have crystallized during that period, very early part of 4.29 to 4.57 gigaannum, from a magma ocean that is entirely encircling the moon, the magma ocean. From there, they have formed with the cooling of the lunar magma, the heavy, the mafic phases like pyroxene and olivines, they sank into the bottom of the magma, whereas the upper part become very denser in that plagioclases. So top 50 to 80 kilometer of the primordial lunar crust is considered to be comprising of the anorthosite. So this is simply segregation with the cooling of the magma, the original, the parental magma is nothing but our chondrite, whatever we see in the chondritic meteorites. The composition of the initial moon was chondritic, that are same as the chondritic meteorites, with the crystallization and evolution, the upper part become feldspar rich and become anorthositic. Now, coming to two very important aspects of types of anorthosites of the terrestrial rocks, that is Archean anorthosite and Petrozoic massive type anorthosite. As you can see here, their age restriction of Archean is from 3.8 to 2.5 GA, whereas Petrozoic anorthosites are reported between 2.5 to 5 0.5 GA. Whereas the Archean anorthosites are dominated by calcium-rich plagioclases, which are normally equant shaped to spherical shaped megacrest. They are more than 4 to 6 centimeter in size, having the composition of feldspars, plagioclases, and content more or less 80, and content 80 plus or minus 10, like that. Whereas protozoic anorthosites, that is massive type anorthosites, are averaging N 50 plus or minus 10. The Archean anorthosites are normally small, generally small in size, less than 100 square kilometer, whereas the largest known is 2,000 square kilometer, whereas massive type anorthosites are generally big complexes. Archean anorthosites, they occur in sill-like bodies, whereas the protozoic anorthosites, they occur as domal or composite plutons. That's why the term massive has come into this, and they are known as massive type anorthosite. Both of them, say, Archean anorthosites are associated with gabbro-peridotite pyroxenite kind of pyroxene or olivine-rich rocks also, whereas proterozoic anorthosites are known to be associated with rocks like charnockite, monzonite, cyanides, and another iron-rich rocks like ferrodyrite, like this. So this is the two major, I have made into a tabular form to give you a brief idea about the two kinds of anorthosites. So these are written for that purpose only. When I said that, so I need not go into details of this. The Archean anorthosites, as you can see, these are megacrest, and these are also cumulates, but the plagioclases are very rich in calcium, whereas the intercumulus phases are like any other case, it is pyroxene or olivine. They do contain some amount of iron, titanium oxides, ilmenites, or chromides, like that. These Archean anorthosites are widely interpreted to crystallize from basaltic parental melt only. But how come such calcic plagioclases are formed? To explain this, actually petrogenetic characters as well as experimental petrology indicates that when the basaltic magma is enriched in H2O, they can crystallize enriched calcic-rich plagioclase megacrest. So this is said to be that the Archean anorthosites have formed in an oceanic art settings. As you can see here, one more thing that I have forgot to tell, that these Archean anorthosites are part and parcel of greenstone belts, Archean greenstone belts. So we know that in greenstone belts we definitely see meta basalts like the kind of thing. These are genetically linked. So the theory is that they are formed from the basaltic parental melt, which was slightly rich in, enriched in H2O, and they are formed in oceanic arc settings. That's why the calcic plagioclases, highly calcic plagioclases have been formed, and at the same time they grown into a larger sizes, because H2O presence also leads to the crystal growth so they tend to be larger in size. The another major type of anorthosite that is occurring in the terrestrial Earth's crust, they, as I said, they are proterozoic massive type anorthosites. They are restricted to the age range of 500 to 2,600 million years. They are really large in size, and they contain also tabular shaped plagioclases, but moderately calcic, not very highly calcic. But these are also cumulate rocks with intercumulus pyroxenes and olivines. They are also associated with gabbro, leuconorite or leucotroctolites, and the accessory mineral phases in all kind of anorthosite is the same, mostly FETA oxides or apatites like that. But one thing that is very interesting to know is that some of these massive type anorthosites, they contain some mega crystal of high alumina orthopyroxenes. These orthopyroxenes, they contain very high Al or alumina, which is almost 10% by weight Al2O3, and this has some pathogenic sign. This indicates the alumina content in pyroxene is indicator of high pressure. That means these rocks must have formed at a depth, high depth. Then only this kind of aluminium can be will be formed in the pyroxenes. So this is a pathogenic indicator of HOM, that is high alumina orthopyroxene megacrystal. Another thing is that, as I said earlier also, that these massive type anorthosites are also associated with rocks like mangarite, chamnokite, granite, such kind of silica-rich plutonic rocks, and collectively they are called as AMCG complexes. So if we come to this, that massive type anorthosites, they themselves are associated with anorthosite, leuconorite, gabbro, or olivine-rich norite, ferrodyrite, jotunite, mangarite, things like this. They are also accompanied by rocks like mangarite, chanokite, granite, and as a whole they constitute AMCG complexes. Now the question is whether they are spatially and temporally and genetically related. That though they are emplaced during a restricted time period, and they are mostly restricted to also high grade belts across the world. So much of work was devoted to understand this genetic or non, whether they are coeval in nature or only coeval, non-co-magmatic, or co-magmatic in nature. And what was the parent magma for these anorthosite and MCG suit of rocks? So it has been works across the world, including some of our works also indicated that based on the field relation mineralogy, trace element, and radiogenic stable isotope studies, it has been now said that there is no direct genetic link between these anorthositic rocks and the silica-rich, granitic or manganite-rich rocks, but they are coeval in nature. They are not co-magmatic, but they are coeval in nature. That we will be discussing. And the other things, normally they come from what kind of parent magma they have formed, what is the mode of emplacement, what is the tectonic environment of their formation, like this. So in this case, I would like to bring your kind attention towards the work that we have been carried out and in context to the Orissa. So we have, this is a map of Eastern Ghat mobile belt, that is a lithojonation map, that is main work of our Jekananda sir and his co-associates. This map, in Eastern Ghats, the anorthosite rocks are located at these places, that is at Chilika Lake, one is at Bolangir, another is Turkel, another is Jugsai Patna, very close to it, Rajendra Nagar, Then another is at Udayagiri. So as you can see from their disposition, they are mostly close to the craton boundaries and excepting the Chilika Lake, of course. But we should not forget that this is in the continuation of the Antarctica belt, Napier as well as our Rainer complexes. This thing should be noted now. The location in Odisha geological map you can see here. They are distributed in such a way. Uh, this is your Bastar pattern and contact, and this side it is Rengali or Singhbum contact. Some of our works, that is, we have worked in Turkel complex, Juksai Patna complex, and Udayagiri complex. And previously, our predecessors have worked in the Balangir as well as Chilka Lake. I'm not going into their details, but these are the geological maps that we have mapped. Me, my co-authors, and my co-workers, and under the supervision of our Jekananda sir. This, as you can see, the core part is, in case of the Turkel, the core part is occupied by anorthositic rocks, whereas the southern rim parts are occupied by ferrodiorite or leucogabbro, leuconorite, things like that. And the northern side, it is the mangaritic rock. Mangaritic is nothing but a kind of chanokite, which is containing both OPX and CPX. Their SiO2 is slightly less than the Charnokite, to be very specific. And as you can see in the Juksai Patna area, same thing, anorthosite occupies at the core of the massif, rimmed by our rocks like leuconorite, leucogabbro. Still, further to that, it is troctolitic rocks. And here we also found some very interesting rocks like eucritic gabbronorite with very high calcic plagioclases. And another very small body of anorthosite was also reported by our work during our work. That is near Udayagiri, that is just north of Dhenkanal. So these are the characters of independent, different complexes. It's a Turkel complex. It's mostly the entire complex is about 150 square, 200 square kilometer area, where anorthosite and leuconorite comprises about 80 square kilometer. And this is the, mineralogy of these rocks comprising of plagioclases, and you can see some all these bodies, they are being emplaced within the Eastern Ghat mobile belt. They are also suffered metamorphism. So the grain margin recrystallization is always there. Some metamorphic reactions leading to formation of the coronal garnet is also noticed. Deformation has also led to the band twinnings in the of the lamellis. So such kind of things are very common in the anorthotic rocks of massive type anorthotic rocks. And you can see here the mangarite. The mangarites are nothing but compositional. They are also chernopitic rocks only, but they are more iron enriched, and they contains both OPX and CPX. Sometimes they are also metamorphosed, formation of garnet, and breakdown of the pyroxenes and development of phyllite plus quartz, such kind of textures. I am just browsing through the pictures which are very typical of the, we saw very typical textures in such rocks. This olivine norite that we have reported, these are more or less, it preserves the magmatic texture, where we had seen the symplectic intergrowth of spinel plagioclase and CPX at the margin of plagioclases. So such kind of textures are very typical, and it also preserves igneous textures. Juksai Patna, as I already said, it's also a semicircular body with anorthosite at the core, and surrounded by a larger portion of the leuconorites, basically leuconorites with very small amount of leucogabbro. And as you can see here, in some places we also noticed alignment of the pyroxenes and feldspars. Here, the more or less similar textures we have found: plagioclase, pyroxene, cumulus plagioclases and intercumulus pyroxenes. And this rock is also suffered metamorphism, so metamorphic features are there. Another typical thing that we have noticed here is the presence of ferrodiorite dikes. These are kind of they are interpreted to be residual liquids after the crystallization of the anorthosite. Whatever the residual liquid is there, they become very rich in HFSC, apatite, zircon, things like that, and very iron-rich rocks also. And these later on they intrude into the complex, and they form dike-like things. As you can see, the branching and anastomosing dikes that is intruding into the anorthosite and leuconorite rocks. This is just a small sketch of the thing that I would like to emphasize, that the N content of the, that means anorthitic content of the plagioclases in different rocks like anorthosite, leuconorite, and ferrodiorite, they change. Actually, there is a mistake here. The top picture should be anorthosite with more iron content, and the lower picture belongs to ferrodiorite with less anorthite content. So these are the two things that set up figures representing the plagioclase composition in Turkana and Juxaipatna. We have just this is common thing that I have already said most of the things. One more thing that I would like to emphasize is that we have reported high alumina gabbro. This has an petrogenic significance that they possibly represent the parental melt composition of the massive type anorthosite complex. So in Juxaipatna, we have reported the presence of high alumina gabbros. And in both Turkana as well as Juxaipatna, we have reported presence of ferrodiorites. These are the residual liquids. They represent the residual liquids. All the complexes are deformed and more or less similar compositional. And one more thing that is very important here to in fact, I have given here that chondrite normalized RE plots for Turkana and Juxaipatna for the rocks like anorthosite and its series, that is leucogabbro, leuconorite, and this. You can see here positive U anomaly for anorthosite, leuconorite, norite, and things like that, and a complementary negative European anomaly for ferrodioritic rocks in both the complexes. Whereas the mangarite and mangarite rocks, suit of rocks, they do not show any strong negative or anomaly, or like they show no European anomaly to mild negative European anomaly, and they appears to be, the pattern appears to be completely different from the gabbro anorthosite ferrodiorite series. So now coming to so with this background, I have tried to discuss the characters of the massive type anorthosite with respect to the Odisha both the complexes of Odisha where we have worked. The same thing has been reported by different workers at different places. We have not done isotopic studies, but people have done isotopic studies also. So they are also similar to the inferences are more or less similar to what we have done through petrology and geochemistry. Here I would like to emphasize one more thing, that so based on all the works that have been carried out across the world, as well the authority of anorthosite, massive type anorthosite and anorthosite in general, he has proposed a concept how these anorthositic massive type anorthosites have been formed. So as per his and most of the cases they also support the geochemistry, mineralogy, as well as the field relation also. This is more or less widely accepted now. So what happens? Initially the magma generates from the mantle, and they get underplated at the mantle crust boundary. They make a pond kind of thing, that is the moho boundary, crust mantle boundary. And with evolution, what happens? The more mafic phases like olivine and pyroxenes, they crystallize and they sink to the bottom of the magma pool. And the at the same time, because of this heat of this magma pond, the lower crustal material also gets melted. And now, because of heat dissipation and fractionation of olivine and pyroxene, the composition of the magma becomes more aluminous and less in FEMG ratio, more FEMG ratio, more less magnesium, more ferrous. So, and there is also, because of the assimilation of the crustal melt, the composition becomes suitable for the crystallization of the plagioclases. And those plagioclases, they are lighter in weight compared to the melt or residual melt. What they do is they now, because of their buoyancy, less denser nature, they rise as a crystal mass and make plutonic bodies somewhere at the mid-crustal level. And these crystal masses, over a period of time, they coalesce and they become larger plutons or massive type anorthosites. And at the same time, the lower crustal the melt, which is more or less granitic or charnokitic in composition, they also surround the anorthositic rocks. So at the same, that's why we see the AMCG complexes, that is anorthosite, mangarite, charnokite, and granite rocks together in massive type anorthositic complexes. Now coming to the ore deposits, as we understand that these are not much significant, but you can see that FETI oxides, they have been reported in many of the massive type anorthosites, just like in TVM bodies, in the large mafic intrusions. In case of massive type anorthosite, some places the titanium becomes richer, and they form the ore deposits, whereas LMIs are rich in vanadium. These massive type anorthosites are poorer in vanadium but rich in titanium. So, taking analogy from the TVM, what we understand titanium vanadiferous magnetite bodies in LMI is similar FETI oxides and nickel. That is very important. Nickel have been reported with the leucocritic cabronorite bodies that are associated with the plagioclases. And the Nan anorthosite suite, that is Norway, that is the best example where nickel is associated with the troctolite. And nickel and cobalt, they are possible. It is possible that if somebody works in the future and look at the mafic rocks, they must see at the nickel and cobalt concentration of the such kind of mafic, gabbroic or neritic rocks that are associated with the anorthosites. Now I have more or less covered, though it is very brief, anorthositic rocks. And now I am moving to the alkaline rocks. Everybody knows the alkaline rocks are nothing but the chemically they may be defined that these are highly alkalic compared to the silica. So they are termed as alkaline. And these alkaline magma series, that because these also have a series of rocks which are chemically related and petrogenetically also related. They contain very high K2O plus Na2O relative to the silica. And these include, when the chemistry becomes like this, therefore, we are likely to get either modal or normative nephlins, leucite, sodic pyroxene, sodic amphiboles, like things like this. So when nephlin or leucite, feldspathoids, basically feldspathoids and sodic pyroxenes and amphiboles are present, the obviously the rock will be undersaturated with silica or quartz absent rocks. These are called as alkaline rocks, and these include many kind of rocks, uh, like nephlin cyanides or nephlin cyanides and cyanides and other series of rocks. But moreover, one more rock, though that is not rich in sodium and potassium, carbonatite, which is basically a carbonate of magnesium or calcium, that is also grouped in these alkaline rocks. Together with the alkaline rocks and carbonatites, these are termed as ARCs, alkaline rocks and carbonatite, ARCs. Most of the cases they are deformed. So a concept like dark, DARC, has come into picture by Burke et al. Now, to plot them chemically, as you can see here, this line in the task diagram, this is total alkali and silica diagram. This divides the subalkaline rocks from the alkaline rocks, and all the above rocks, that is cyanide, nephlin cyanides, these are plutonic. They do have also volcanic equivalents. Cyanide, cyanodiorite, zeolite, and alkali gabbro, all these constitute chemically alkaline rocks. And besides that, as I said, this is the chemical diagram for carbonatites, where the dominant, as I said, is magnesium and calcium with carbonate. Then this is very rich in calcium, then it is calciocarbonate, and one axis is magnesium, that is magnesiocarbonate, another axis is iron, that is ferrocarbonatite. So two axes, pure carbonatite, two magnesium or iron rich carbonatites are also there. So this is the chemical characterization for the alkaline rocks. And if I come to the mineralogical aspects, the upper part, AFP diagram, that constitutes the plutonic part, and the lower part that represents the volcanic part. So different names like trachyte, latite, andesite basalt, phonolite, tephrite, these are the volcanic alkaline rocks, and these are silicates. Please try to distinguish between carbonatites and silicates, alkaline silicates. So these are silicates with feldspathoid, and lower one is volcanic and upper one is our plutonic. So many important rocks include basanites, tephrites, phonolites, leucites, nephlinites, and the other one non-silicate is a carbonatite. These are the important alkaline rocks that we normally see in the alkaline complexes. The right side top picture that shows the compositional range of different carbonatite rocks that have been reported in India. Like some parts in Rajasthan, some in Tamil Nadu. So we can see the different carbonatite bodies have a different compositional range. This has a bearing for RE mineralization also. Some pictures, some carbonatites reported from Afghanistan, Pakistan, and Sri Lanka is also here. Now, to understand the one typical character of the volcanic alkaline rocks is that they are normally porphyritic. We will find the porphyritic nature very significant in case of volcanic alkaline rocks, as I showing in the photographs. The lower one represents carbonatite. Here you can see mostly it is calcitic, calcite. This is also a cumulate with calcite, and some may be dolomitic also. And this shows the distribution of alkaline rocks in India. Coming to Indian context, you can see the Great Indian Proterozoic Fold Belt, that is following from the Aravalli to Central Indian Tectonic Zone to Eastern Ghats, and then uh, uh, the lower part is obviously that Southern Granite terrain. So at least 60 alkaline complexes of alkaline silicate rocks or carbonatites have been reported from different states, out of which about 47 they are from the GIPB, GIPFB, and the remaining majority are in the southern granite terrain, and they are concentrated at the contact between Dhorvars and SGT. As you can see here, this contact, or they are within the SGT, that is we call as a Dharmapuri rift zone. They are concentrated is that Dharmapuri rift zone. So, see, this is the distribution of alkaline rocks. Coming to Odisha context, I will come with a more larger picture for Odisha context. So, this just to indicate important alkaline complexes reported across the world. You can see here three bigger stars. The southern one is Gunlupet, that GSI has just explored to up to G4, G2 stage in thing 2 years back, and the officers have also awarded with Geoscience Award for this work. This is a new kind of report, as I can now tell you that this is occurring at the contact between Dharwar and CSGT. Actually, the alkaline carbonatite rocks and alkaline complexes, they are well known in the Dharmapuri rift zone since many years, many decades. But the occurrence of carbonatite rocks at the contact between the Dharwar and SGT, that was recently reported, and one of such is our Gundlupet. That Gundlupet has GSI has worked recently, and we have developed from G4 to G3 to G2 stage investigation. And one more important is Rambaji, everybody knows, in the Delhi Fold Belt, and Khajra, that is one there. And there are several others, very important things. As the important thing is that Kamathai in Rajasthan, it is the only a non RE deposit till date still, but Ambadangar is coming up, and it will be it is being worked by both GSI as well as AMD. A very important thing is that how they are formed and what is the tectonic setting. So it is very well established from all considerations: petrological, field relation, geochemical, and isotopic. All consideration, it has been told that there are postulated that the alkaline rocks and carbonatites, they form in the extensional tectonic settings, that is in the rift settings, where what happens in the rift setting, that there is always a low degree of partial melting that takes place in the mantle. And now the thing is that the complex or the variety of rock types we encounter in any alkaline complex, like we can see carbonatites or cyanides or nepheline cyanides or leucites or tephrites, such kind of compositions, they derive because of the source and the nature of the mantle. Say the mantle must be metasomatized and enriched, And partial melting of enriched metasomatized mantle will definitely lead to formation. And low degree, very important, low degree, less than 5% partial melt will lead to the development of the alkaline rocks. See, these alkaline rocks, they generally form from the upper mental thing. But the thing is that there are several theories, whether uh, low degree of partial melting from mantle, that is asthenospheric mantle or lithospheric mantle, or there is a crustal contamination. All such things, they lead to develop a series of alkaline rocks because of this. The processes that are postulated are three. Those include liquid immiscibility, fractional crystallization, and low degree of partial melting. Liquid immiscibility is nothing but melt is generated, then they become two immiscible liquids. One is silica melt, another is carbonate rich melt, and they get emplaced in one rock. The silica rich melt becomes the silicate alkaline rocks, whereas carbonate rich rocks become the carbonatite. Another thing is that may involve that is fractional crystallization. A melt is formed, and then from there, because of fractional crystallization, either silicate forms first, making the residual melt reach in carbonate, or a carbonate forms first and the residual melt becomes rich in silicates, and they emplace at some place, forming both rocks. Low degree of partial melting is mandatory. So in most of the cases, all three or at least two are observed in the complexes. Most of the carbonate, alkaline and arcs or darks, we can say. Three more things that is important, that is metasomatism of the mantle. A carbonate metasomatism leads to carbonatite formation at the early stage. And crustal assimilation or contamination is very, very important for mineralization point of view. If the partial melt assimilates or is get contaminated by the lower crustal melt, lower crustal rocks, then it induces mineralization. And phenitization is one more thing, that is the fluid associated with the is magmas. These are fluid-rich magmas. So the fluid rich in these magmas, they also phenitize or they alter the surrounding rocks, and they also become enriched in the REs. This is a picture that to show, this is not very important for this kind of thing, that here I am trying to tell that the resource position and production of REs from different countries. As you can see, China dominates about 80%, and the rest comprises about 20% in the RE reserves. And the another thing is that REs can be obtained from carbonatites, from alkaline igneous systems, or by ion absorption in the clays also, and maybe monotherm in the placer deposits also. So these four axes, basically we call it is a four axes, they may lead us to any RE deposit. So our search for mineralization is in four these things. This is the distribution of RE deposits in the world picture. As you can see here, this is the solid are basically the active mines. Solid colors are active mines, whereas the and not filled. Filled ones are active mines, whereas unfilled are advanced projects. They will be coming up very recently. And moreover, as you can from see here also, you can see the four axes that we are trying to tell, that is carbonatite axis one, and for alkaline igneous rocks, alkaline igneous silicate, cyanide kind of rocks or their volcanic equivalents, then the heavy mineral sands and clays. So these colors, different colors represent different parts, and now coming to Odisha specific, As you can see here, this is a picture that is taken from Sheikh et al. 2022, who have published recently reported one alkaline complex in the northern contact, that is Rengali and Protogic Eastern Ghats. So here, somewhere here, you can see this part represents the western side is Bastar Craton, and northern part is Rengali and Singhbum Craton, and the stars we can see here, the stars, the stars are the locations of the different alkaline complex that has been reported till in Odisha. This is Koraput, and then Bolangir, this entire thing is basically not Bolangir. This entire thing is Courier complex, and followed by that, you can see here, this is one can see that our Redakal sector, and this part is mostly our this Borodangwa and that east sector that have been reported now, that is Chakpar, like that. This is one geological map of Redakal, Riamal, Rengali sector, where you can see here one major alkaline complex that is marked in the red, that is here near Redakal. And there are several small bodies of alkaline rocks have been reported from this that is what is that? I just forgot the name now. In this sector, this is Kokodakol and Lodhadri sector. So these bodies are very. One thing that I would like to emphasize here is that till now, no carbonatite has been reported from Odisha sector, but we have reported, and people have reported, many alkaline silicate rocks, mainly our nepheline cyanite and associated rocks. These are some of the alkaline silicate nepheline cyanite rocks in Raidakol and Kokodakol Ladajari alkaline complex. You can see here, these are all deformed alkaline complexes, and this is some from Korea, and this the lower left right is basically a sapphire, gem quality sapphire that is associated with blue sapphire associated with alkaline nepheline cyanide, and this is a Courier alkaline complex, and me and my co-workers have worked in this segment where our contribution, people have mapped this and many things have been done, but mainly our contribution is to say that here there is a multiple intrusions. You can say that you can see here, majority of the alkaline rocks here, that is cyanitic or nepheline cyanides here, are deformed. But there are patches, there are bodies where there is no deformation. You can see the magmatic signature is there, and some are fine grained too, some are megacrystic also, and these are intrusive into deformed ones. So that's why we, based on the field evidences, we have reported that there is a multiple time emplacement of the this kind the here Courier complex, nepheline cyanide intrusion, and here also there is a controversy on the dating aspect, where the one group of workers have reported about 1350 million years, another group of workers have reported about 550 million years. So though we have not dated, we understand that the earlier phase was 1350 and the later phase was 550 million years. Now coming to one more thing, that is the alkaline rocks or the silicate rocks of Odisha sector, they are not reported to have REs. But many of the cases, world or maybe other cases, they are associated with REs. So there must be some consideration why this rock is, Odisha rocks are not having and other rocks are having. So one more thing is that the Na by K ratio, Na plus K by aluminum ratio has to be extremely high, more than 1.2. That apacitic rock, there is to be apacitic. Miascitic rocks are not supposed to be RE rich because these are more alkaline. At the same time, such rocks are associated with fractionation. This fractionation is the concept that leads to the RE fractionation on the very late stage. So if the rocks are ecpytitic, where Na plus K by Al2 ratio is more than 1.2 and rocks are associated with fractionation, then they are likely to be RE bearing rocks or RE rich rocks, maybe forming to in some kind of differential deposits or occurrences. And another thing is that overall, the RE content of the nepheline cyanides or silicate alkaline rocks is more lesser than that of carbonatites, lower than that of the carbonatites. They are also LRE rich. But more important thing is that sometimes the alkaline silicate alkaline rocks, they contain more HRE compared to the carbonatite. So HRE is also very important aspect in the world. When it has larger use compared to the LRE. So alkaline silicate rocks, they have HRE more than the carbonatites reported occurrences. So these such kind of rocks, the nepheline cyanides and as the series of rocks that have been reported elsewhere, they do one only active mine is now in Russia, that is that produces loparite. That is one mineral that you can see the formula written here. That is peroxide series, and they are also source of niobium and RE. So one more thing that I would like to tell that till now, as in the world, these kind of these countries have the known deposits are these, and as you can see along with the China, Bayanobo, the largest RE deposit, RENBFE deposits, largest known till date, Bayanobo. This is nothing but an igneous carbonatite complex. So four axes that I had told earlier, that carbonatite, alkaline igneous rocks, silicate igneous rocks, placers, and the other one is clay. And so these are the different deposits, and these are different types. So I can see in Turkey we have a placer RE deposit. Here in Andhra we have also worked in Telangana, that is we have also tried to work for placers. Placers are always associated in the coastal belts, and Gondwana here in Andhra Telangana, Gondwanas are reported to contain REs, the monazite-like minerals. They are rich in RE. That has also been worked or work has been going on, and some work has also been done. This is not very important for today's thing, and these are this right side table that shows the different RE minerals and their formulas like allanite, apatite, bastanosite. These are very important for any RE deposit. Carbonatites are normally associated with bastanite, apatite, and one more thing is that fluorite may be there. That fluorides are also very rich in RE. So this kind of mineralogy that leads to a pyrochlore. Pyrochlore is another important mineral. These are all very important RE bearing minerals that are associated with the carbonatites. So this is all about my presentation today. In brief, I have tried to cover both the aspects, and thank you all. The last slide where I am showing that is that these are relates to the backscattered images of carbonatite complex that I have worked. So just with this, I end my presentation here. Thank you very much.